Okay, this is really just a bit of revision of binomial and Poisson probabilities and means and variances from the AS course. Okay, so this is a binomial and it's got an n and it's got a p, and I've got to work out the mean and the variance. Well, the formulas for mean and variance of a binomial are there on page 13 of your formula book. The mean formula is np and the variance formula is np 1 minus p. And you need to know that it's page 13 that you find those on. Okay, so for this particular one, my mean is going to be 10 times 0.5, which is 5. And my variance is going to be 10 times 0.5 times 1 minus 0.5, which is 0.5 again. So the variance will be 2.5. To get the probability of x being less than or equal to 3, well, I need on my calculator to go into binomial CD. So we never use binomial PD, binomial CD, variable. So I've got loads of rubbish in there at the moment. I want to be less than or equal to 3, so that's all right. I want n to be 10, and I want p to be 0.5. And it's telling me the probability being less than or equal to 3 is 0.1719. 0.1719. Now, to do a range like this, this one I didn't draw the list of outcomes. Maybe I should have done. For this one, I definitely need to. So 0, 1, 2, 3, ... 5, 6, 7, ... and it goes up to 10. So I want, I don't want 0, I don't want 1, I want everything from 2 to 6 inclusive, because these are less than or equal to's. So I don't want 7, I don't want 10. So my first box goes up to and includes the 6, and then I need to get rid of the ones I don't want. So that shows me that I need to do the probability that x is less than or equal to 6 for the big box that I do want. And then I need to get rid of the probability of x being less than or equal to 1. So I can do that on the same screen here to get the values. So less than or equal to 6 is a probability of 0.828. 0.828 minus, well, let's do another decimal place 1. And let's take away the probability of less than or equal to 1. So put 1 in here. So that's minus 0.0107. And if I subtract those, we get 0.8174. 0.8174 is my answer. Okay, so the rest of the table is just a matter of doing the same calculations for lots of different binomial distributions. So let's go down the columns. The next one, my n is 50 and my p is 0.1, so I'm doing 50 times 0.1, which is 5, and 500 for this one times 0.001, that's 0.01 it should be, sorry, equals, 5 again, and this one 5,000 times 0.001 equals 5, and this one times this one is 5, this one times this one is 5. Now on the last row I've got a Poisson distribution with a mean of 5. Oh, and this isn't quite right. This should say PO5. Okay, must put that right in the booklet. Okay, Poisson distribution with mean of 5. Okay, and that's why all of these binomials were chosen. So we've got lots of different binomials, all with the same mean. Okay, moving on to the variances, the next row down, NPQ will, NP1 minus P will be 50 times 0.1 again, but now I need to, my 1 minus P will be times 0.9, so I'm going to get 50 times 0.1 times 0.9 is actually 4.5, and when I work out the other ones in the similar sort of way, the next one I get N times p of 0.01 times 1 minus p of 0.99, and that equals 4.95. And if you do the other ones, you'll get 4.995 and 4.9995. Fairly obvious pattern. This one is going to be this. Okay, by all means check all of these details. Okay, now going back to page 13 of your formula book, okay, and your knowledge from last year, we know that when we have the mean of a Poisson being 5, the variance, not the standard deviation, but the variance is always the same thing, value as the mean. So we can see that as our binomials go down along this sequence, they've all got the same mean, and the variance is getting closer and closer to 5. Now let's look at what happens when I work out a probability of a particular range, like being less than or equal to 3. So I've already done that for the first one. Let's do that the same thing with binomial CD for the next one with an n of 50 and a p of 0.1. So here we go, menu 7, second menu, binomial CD. Okay, so that's the screen I need. I need an x value of, I want to be less than or equal to 3, and I've got an n value now of 50 and a p of 0.1, and the probability I get for that is 0.2503. Okay, ready to do the next one. So I'm going to have an x value of 3, I'm going to have an n now of 500, I'm going to have a p value of 0.01, and I'm going to get a probability, and that probability is now 0.2636. And I'm going to do it again with an n value of 5,000 and a p value of 0.001, and I'm going to get a probability of 0.2649. And I'm going to do it again with an n value of 50,000 and a p value of 0.0001, and it's going to give me 0.2650. And for that last one here, set up here, probability is 0.2650 again. Slightly different places after that, but they agree to 4 significant figures. Okay, so these values first two are a bit different, but after that they started staying remarkably the same. So now let's actually try the Poisson probability with a Poisson of mean 5 of being less than or equal to 3. So I need to do menu 7, and now I need to find Poisson CD, which is 3. Okay, and I need to do mean has got to be 5. Okay, no, the x value is 3. The mean is 5, which is lambda. Okay, and it tells me the probability of being less than or equal to 3 on a Poisson is, okay, 0.2650. Okay, so we haven't actually kept the decimal places here and here, but I can see they've got remarkably close. So means have always been 5. The variances have been getting closer and closer to 5. Okay, and the probability calculated, this is just one chosen at random pretty much, x being less than or equal to 3, that's getting closer and closer to the Poisson probability as I go through this sequence of binomials. Yeah, and we can now look at what happens to this probability here, which is a bit more tedious because we have to work out a subtraction of 2 values, but let's do that. Well, I've used the table feature. This says 6 and 1 for the 2x values. I've entered the correct values for n and p, and it's telling me that the 2 probabilities I need to subtract for the second row are 0.7702, and I need to take away 0.0337, and that gives me 0.7365, not very well written, but there it is. And we can use the same method to work out all the other ones, okay? Well, I've actually cheated and done this on Excel, so the next one turns out to be 0.7232, and then 0.7219, and 0.7218, and 0.72175, which also rounds to 18, and we can see we're getting the same kind of convergence here. So we're just going to do the same thing for the Poisson. So if I go into my Poisson CD, and I have to do the same subtraction, I'm going to use the list feature again. So I'm going to want probabilities of 6 and 1, and they are correctly set up, and I'm going to want my lambda value of 5, which is correctly set up. So my probabilities to subtract are 0.7 621 minus 0.0404, and if I take those two away, I get 0.7217. That should have been dreadful job I did of writing that. 7217. So that's the answer, and we can see that the binomial values once again are all getting closer and closer to the Poisson distribution. So what I notice is that if I restrict my attention to binomial distributions, remember what they had in common was a mean of 5, then as n gets very, very large and p gets very, very small, keeping a mean of 5, then all the answers I get for everything, for variance and for probabilities from the binomial distributions, they get very, very close to a Poisson distribution with the same mean. So that's my comment. So I can record that as for large n and small p, binomial probabilities become very close to the corresponding probabilities from a Poisson distribution with the same mean. And this is the basis for the Poisson approximation to the binomial distribution.